Okay, now we're going to use the parallel axis theorem to verify our formula for alpha, the angular acceleration of this hoop as it rolls down an inclined plane of angle theta. If you remember, I'll just do this in, okay. If you remember from the last time we did this, we were trying to figure out alpha, and there was only a handful of equations that even had alpha in them. So it was this, or it was going to be this, or it's going to be this. And, it's not a kinematic equation, but, this times this was equal to that. That's not, it has alpha in it, but anyways. We were trying to figure out what alpha was. We don't have the time it takes to roll down the ramp. We certainly don't have the linear acceleration it took to roll down the ramp, so we couldn't use those two. And what I said was that you can use either of these two equations. The only thing you want to ask yourself is it going to be easier to figure out what the angular displacement will be as it rolls down? Or is it going to be easier to figure out what exactly is the torque and what exactly is the moment of inertia for a hoop rolling down a ramp? Right? Either one will get you the correct alpha, but we used this one because it was way easier. But today what we're going to do is we're going to use this one to verify what our formula for alpha was by using the parallel axis theorem, PAT. If you remember, what we actually got the other day for our formula for angular acceleration down the ramp was that alpha turned out to be g sine theta all over 2r, right, where of course r was that. So this is what we're trying to get to. All right, this is a proof. All right, so let's start with this hoop. We're going to start with this idea that torque is equal to the moment of inertia times alpha, which, torque divided by moment of inertia will be the alpha. So we got two issues. What is the torque? Not particularly obvious. It's not going to be that. It's not a slam dunk what that is. And I. So let's just start with what we know, what we're practicing today, which is the parallel axis theorem. Okay. The moment of inertia for this hoop as it rolls down. I'm going to zoom in here for a moment. The moment of inertia for this hoop, well, let me take a step back here. The first thing we have to figure out is, well, let's just the moment. We'll call this. Well, this is the parallel axis theorem. Okay, let's just jump to that. The question is what is this for a hoop rolling down the ramp? Now, you might think, and this is not a bad initial thought, is that this hoop will rotate about its center of mass. The axis of rotation will be through the center of mass. In which case, oh, no, this term just goes to zero. We're not even going to have it. It's just, remember, the center of mass for a hoop was mr squared. All right, so you might be tempted to think it's just that. However, that's actually not the case. And this is a idea that is not obvious at all, but which is, I'm going to zoom in a little bit down here. Make this a little bit bigger. Okay. The first thing is, as this thing rolls down the ramp, where is the axis of rotation? It turns out that the axis of rotation is actually right here. If you're not sure why that is, let's just do a little mental exercise. Let's pretend that there is no rest of this ramp right here. Let's just for a moment pretend, and I'm going to credit Mr. Killian for giving me this little mental trick, because my explanation was correct, but a little bit lengthier and had more pictures. I like his because it's short and sweet. If there's no rest of the ramp, about which axis will this thing rotate about as it moves? Is it going to continue to rotate around here, or is it going to swing around this axis? And now you can see that it seems pretty obvious that the axis of rotation is really there at the connection or the intersection point between the rim and the ramp. Again, not an obvious thing to see, But it turns out, again, that the axis of rotation is not through the center of mass. It is actually through that intersection point. So let me just finish my back there. Okay. So zoom out a bit again. Sorry, I guess I didn't zoom out enough. Here we go. Let's try it again. So the I value, is going to be, now for hoop, it's mr squared. And now this piece right there also has a distance of r away from the center of mass. So it's going to be an additional piece of mr squared for a grand total of 2mr squared. That takes care of the I. Now let's think about the torque. I'm going to zoom in again. Remember that, let's do torque in blue. Torque is equal to F times R. What force? So we got to, what is the force causing this rotation? Again, not obvious. What we're going to do is I'm going to start with creating sort of our force triangles that we always do on ramps, and see if this will see if this will bear some fruit, as they say. This vector down here is mg. This vector up there is the normal force, mg cos theta. Of course, the ramp, I already have the theta, good. And this one down the ramp is mg sine theta. Okay, so which one of these three is going to cause the torque? The initial temptation is to use the mg force of gravity applied at a distance of r. So the initial temptation is to go to mgr. However, this thing is accelerating this way down the ramp. It is not accelerating straight down. So it can't simply be mg. What we got to figure out is what is the force causing the rotation, and this is, again, not obvious. Turns out, if you think about it, it is the frictional force here that causes the rotation. If there's no friction, then this thing simply translates or slides down the ramp without rotating. So it is the frictional force that causes the rotation. And here's where some people will call this cheating, some people will call this clever, but here's where we have to do something we do a lot in physics, which is a sort of approximation, or technically it's called limits, but we will assume that there is enough frictional force to cause the rotation. However, we will also assume that the energy lost due to the force of friction is zero. Well, those two are actually two contradictory terms, two contradictory ideas. How can you have a force of friction and yet have that force of friction have no loss of energy? We do this types of approximation all the time in physics when we say, okay, what force do you have to push a box to get it to start to overcome friction, right? And we set the force of the push equal to the static frictional force. Well, technically, that gives you an acceleration of zero. We just know that any small amount above that gives you an acceleration. So it's a sense of limits. It's the same idea that we're going to use here. So that's my sort of justification for not losing any energy to force of friction, but it still exists. Newton's third law says that if there's a force this way, there's an equal and opposite force this way. And that term, it turns out, if that's true, that means that the force of friction must be equal to mg sine theta in terms of its magnitude. Now, obviously, that's not how you would calculate it. If you wanted to calculate a number for the force of friction, you would need things like mu and mg cos theta. You would need mu for sure. But we just know that in magnitude, it has to be equal to mg sine theta. So the torque is really equal to mg sine theta times r. Again, this is not obvious, which is why we didn't go this route the other day. We used the omega f squared route. That was way easier. But now we can combine these two ideas. We're going back to here. So mg sine theta r is the torque, over 2mr squared is the moment of inertia, and that is equal to alpha. And so we end up with g sine theta all over 2r, and that is exactly what we wanted to get right there. So that makes us happy. So while this is not the typical way you would go about solving for alpha, because there's way more obstacles using this one. I mean, you'd have to apply the parallel axis theorem correctly. You'd also have to figure out exactly what the torque is and what that is. But you could do it and you could get alpha. In practice, if I'm taking an AP test, I'm going this route because that is way easier to get it. There's less obstacles to jump through. But anyways, that's how we could use the parallel axis theorem to verify an angular acceleration that we calculated using kinematics.